In this video, we'll talk about dot product. So the definition is given two non-zero vectors u and v in 2 or 3 dimensions. Their dot product is u dot product v, so the notation is just a dot, equals magnitude of u times magnitude of v times cosine theta. So basically, if I have two vectors, vector u and vector v, with theta between them, then I can find their dot product. So where theta is the angle between u and v, and it's an angle between 0 and pi. So in other words, the result will be a number or a scalar. Definition: orthogonal vectors. So if we have two vectors u and v, they are orthogonal if and only if their dot product is 0. So if we think about it, cosine of pi over 2 or cosine of 90 degrees is 0. So our vectors must be perpendicular to have cosine of 90 degrees in their dot product. So if two vectors are perpendicular, their dot product is 0. If the dot product is 0, then the vectors are perpendicular. Let's look at the dot product theorem. Given u, the vector u in the component form u1, u2, u3, and v as v1, v2, v3, the dot product of u and v is u1, v1 plus u2, v2 plus u3, v3. So in order to prove that, let's recall law of cosine. So that says if we have a triangle ABC with the angle between A and B theta, C squared is equal to A squared plus B squared minus 2AB cosine theta. So in our case, if I consider this vector u, this vector v, and this vector u minus v, because this is the endpoint, then we can say u minus v, or the magnitude of u minus v squared is u squared plus v squared, the magnitude of u, magnitude of v, and then minus 2 magnitude of u, magnitude of v, cosine theta. Now this, we know from the definition of the dot product that it's actually u times v. So let's see what we get. Now u minus v in component form and squared is going to be u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared equals u squared is u1 squared plus u2 squared plus u3 squared. V squared is v1 squared plus v2 squared plus v3 squared minus 2u dot product v. Now if we open up the left hand side using the formula a minus b squared, a squared minus 2ab plus b squared, we have u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared plus u3 squared minus 2u3 v3 plus v3 squared equals u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared minus 2 u dot product v. So we notice that u1 squared cancels with u1 squared, v1 squared with v1 squared, u2 squared with u2 squared, v2 squared with v2 squared, u3 squared with u3 squared, and v3 squared with v3 squared. So what we get is these terms here with a negative 2 in front of them. So we can factor out the negative 2. So we get negative 2 u1 v1 plus u2 v2 plus u3 v3 equals negative 2 u dot v. If we divide by negative 2, we get the dot product of u and v. It's u1 v1 plus u2 v2 plus u3 v3. So we did prove the theorem. So one of the reasons why we learn dot product is because it helps us to find the angle between two vectors. So let's do that. Let's do this example where we have u, it's square root of 3, 1, 0, and v is 1 square root of 3, 0, and w is 1 square root of 3, 2 square root of 3, and they want us to find u times v. So they want us to find the dot product uv. Now we just proved the theorem. If they are written in component form, we just multiply the components. So u times v will be square root of 3 times 1 plus 1 times square root of 3 square root of 3, and then 0. So it's 2 square root of 3. 2 says find the angle between u and v. So we know that u times v is magnitude of u times magnitude of v times cosine theta. We can find the magnitude of u, which is square root of, or we can say, yeah, square root of 3 squared, which is 3 plus 1, so we get 2, and then the magnitude of v is square root of 1 plus square root of 3 squared, that's 3, so we get 2. So if we replace in the dot product formula, is magnitude of u times magnitude of v times cosine theta. So cosine theta is the dot product of u times v over the magnitude of u times magnitude of v. So we get, let's see, u times v, it's 2 square root of 3, and then 2 times 2 found before. So we get square root of 3 over 2. And so theta, it's an angle between 0 and pi. So cosine of what angle? It's square root of 3 over 2 of 30 degrees, which is pi over 6. Let's do part 3. It says find the angle between u and w. So u times w is, so I'm looking at u and w now. So it's square root of 3 times 1 is square root of 3 plus 1 times square root of 3 square root of 3, and the other one is 0, so we get 2 square root of 3. We do know the magnitude of u, but we need to find the magnitude of v. So that's square root of 1 plus 3 plus 12, so that it's square root of 16, which is 4. So cosine of theta is going to be u times v, the dot product, over the magnitude of u times magnitude of w. So it's 2 square root of 3 over magnitude of u was 2 and magnitude of w it's 4. So we get square root of 3 over 4. That means theta, I use the same variable. I could say that this between u and v is theta 1, and let's call this theta 2, is arc cosine of square root of 3 over 4. So that is 64.3 degrees, if we write it as degrees. Or we can change it to radians by multiplying by pi over 180 degrees. So we get 0.36 if we round it to 2 decimals pi, or we can just multiply it with pi and get 1.12 radians. All right. Properties of dot product. If we multiply u times v and v times u, we'll get the same thing. So commutative property. Associative with a scalar. So c times u times v is can be written cu times v, or it can be u times cv. Distributive property, u times v plus w is u times v plus u times w. So another thing that dot product helps us find is the projection of a vector onto another vector. So let's say you have this vector of OP, it's your vector u, it's your vector v. Sorry, this whole thing, the green one is vector v, and this pink one is vector u. The projection, so if you project this endpoint onto v, you're gonna get this OP. It's the projection of u onto v. And if I want to find the length of it, the scalar, it's actually the magnitude of u times cosine theta, and the reason is cosine theta into this right triangle here is adjacent side, which is OP, over, and let's say magnitude over hypotenuse, which is u. So that's why the OP, if you cross multiply, you get OP is u cosine theta. So that's what we have here, but we can also have the vector, it's u, it's directed this way. So when we project it, we get this triangle. So when we calculated actually cosine of this angle, because we are in the second quadrant, this would give us a negative value for cosine. So the magnitude of OP, or this scalar vector, would be negative, which is going to show us the direction of the vector being opposite to the positive one. So this projection of u onto v, using the triangle, right, using this right triangle, if you think about it, is going to be u cosine theta, which was OP basically, but OP, it's in it's magnitude. So that means we add this vector here, v over, is the unit vector in the direction of v, just to give us the projection as a vector. So projection of v over u can be also written as a scalar of u onto v times v over magnitude of v, but this scalar v is can be written, or this whole thing can be written as u times v over v times v times v. And this is because if we do the dot product of a vector with itself, we get v times v in absolute value times cosine of 0, which is 1. So it's equal to v squared. So what happened here is the scalar of u onto v was modulo of u cosine theta, and then times v over v. So if I multiply the numerator and the denominator both by module of v, or absolute value of v, we get at the top this times this. It's exactly u dot product v. The bottom one is absolute value of v squared times v. So at the top we get u times v over v times v, which we just showed up here, so times v. So, or not dot product, just to make a distinction, v like this. So this is the proof of this projection of u onto v can be also written in this form. So we saw that it can be written as a scalar of u onto v times the unit vector in the direction of v. But where is this coming from? This piece here in green? Well, we just prove it from here down. So let's solve a problem. It says for u 3i minus 2j and v for I, find the projection. So projection of u onto of v. Let's make a quick sketch. So u, so xy, u is 1, 2, 3 and negative 2. So basically the vector u is this one. This is vector u. And v is 4i. So 4i. This is vector v. And we want to find the projection of u onto v. So if we project it like this, right, on v, we notice that the projection of u onto v, it's actually 3i. But how do I do that? Now, it was easy to see it from the graph, but how do I do it analytically? So it was easy in the graph, but let's try using the formula. Projection of u onto v is, and let's take a look at the formula, this one, u v, so the dot product of u v over v times v times v. These are dot products and the other one is just multiplying the vectors. So the dot product between u and v is given by multiplying, so u can be written as 3, negative 2, and v can be written 4, 0. So we can just multiply them, these two, and then add with these two. So we get 12 over v times v is multiplying v with itself, so that's 16, times, just times, the vector v, which is 4i. So we get, this cancel with this one, we get 4, 12 over 4, so we get 3i, exactly what we got before. Now, we also had to find the scalar of u over v onto v. So that is actually, if we take a look at the formulas, right, the scalar is given by, the scalar of u onto v is given by the dot product of u times v over v. So scalar is u times v over v. U times v, we found it today. So u times v is 12. And v is absolute value of v. So, and v is 4. So that gives us 3. The scalar of u onto v is just 3. Or we could just calculate the modulus of this, the absolute value. Now let's take a look at the work application in vectors. So let a constant force F be applied to an object producing a displacement d. If the angle between F and D is theta, then the work done by the force is given by the dot product of F and D, of the force and the displacement. So let's take a look at this example. Compute the work done by a force F, written in the component form, so I can say F is 12i plus 9j to move an object 15 meters horizontally. So we can draw here just so that we can see what we are dealing with. So if we say 3, 6, 9, 12, this would be 12i, and this would be 3, 6, 9j. So this would be the force. And we want to move the object 15 meters horizontally. So that means we go 15. So this would be the d, the displacement vector, and this would be the force. So we want to find the work. So the work is given by F times D times cosine theta. So basically theta is the angle between the two. So let's find theta because if we do the projection of F onto D, we notice that we get here a right triangle. So we can say right away that cosine theta is the adjacent side, which is 12, over the hypotenuse, which we can calculate. So the modulus, the magnitude of F squared is equal to 9 squared plus 12 squared. So that is 81 plus 144. That would be 225. So the magnitude of F is 15. So cosine of theta is 12 over 15, which means theta is cosine negative 1 of, we can divide this by 3 and get 4 over 5. So that means I know the magnitude of F. I can find the magnitude of D, which is 15. So the work is 15 times 15 times cosine of cosine negative 1 4 over 5. So we get 225 times 4 over 5. This cancels with this and we get 45. So 45 times 4 is 2180 joules is the work that we need to do by applying the force to move the object 15 meters horizontally.